time for us to start. And as we have, we were discussing last time, and a couple of you asked me what the plans are for the rest of the semester. So here is what I thought we should do. I will not give extra homework. So the one that you just have to return tomorrow will be the last one. I will, however, as we do review this week. And as you will see from the module that I put up for this week, we are gonna review LNAs today and Wednesday. And then we are gonna review filters Friday and Monday before Thanksgiving. And those days that we have a lecture, I will take one of the office hours regularly. The office hours are from 3 to 5. So I will take 1 hour from 3 to 4, and I will solve problems. So for review, for those of you who want to join. And then the other hour, I will leave it just in case students have specific questions they want to talk to me in groups or individually. And every one of the lectures, I will give a question. On Friday, I will give a quiz, so the top hat I'm talking about. And this weekend, the following Sunday, right before our final, I will have a makeup assignment, another one, in case there are students who need to take this makeup assignment. It's gonna be also on a top hat. It's gonna be a similar kind of thing as I did last time. And these are the plans. In terms of the project, I have just submitted one that, and the due date, I believe, is just Friday or Saturday after Thanksgiving.
You mean the Black Friday?
Yeah, why?
It's always Black Friday.
So what do you mean Black Friday? Black Friday is for those who wanna buy something on internet.
Or we can get more points.
I'm sorry. I mean, listen. This semester, I have to remind you, is not like any other regular semester. And you have to understand that. We are squeezing every single day we can because we are finishing earlier.
But we started earlier as well.
Well, we started earlier 2 days. And so 2 lectures. And then we have to make up for like a full week and a half. And so don't nickel and dime me, as they say, I mean, it's for you to do well and to use it. I never had to take any Friday off after Thanksgiving since I remember myself, because my society had a deadline for papers to be submitted the Monday after. So, I mean, don't tell me it's Black Friday. Black Friday is for people who were waiting outside of the stores to buy something. Or for others who want to get on internet and buy stuff at 30% of the price, which I'm not saying is bad, but we are working on Friday.
Okay, so that means the next project assignment is due November 27th.
Yes.
Friday.
Is that a problem with
Saturday
that?
Or no problem. Is it Friday or Saturday?
Excuse me. Now listen, Zahin, please look on eCampus and you will see the deadline.
Okay.
Okay, please do that.
Okay.
Okay, thank you. So the only other thing that I would like you to do is to just put together, and I will ask you sometime this week. I will submit the only other thing I wanted you to do, but the project is to put all of the pieces together not doing any extra work, just take all of your submissions, put them together in a packet and upload it on the eCampus, so for me to have access to it, and I will give you points for that. And this is all we're gonna do before the final. So any questions about this?
One more question. So for a top hat, we have 3 more assignments and 1 more quiz.
Yes.
I see.
Yeah. Okay. I will. What I do. What I also need to. I promise to do, and I unfortunately I don't have that available today. But I will give you a projection now that we are towards. I have to do 2 things. Now that we are close to the end of this semester, one is to give you a projection of these things, to write them down for you, what I just discussed, and then to give you a projection of how many additional points we're going to have. And I will then look from the beginning. That's the second thing I need to do, from the beginning of the semester, and I will give you a projection about what the total, how the total will look like until the end. And I will also upload all of the grades from TopHat. And I know the TA is grading the homework to give you also a feel of where you're gonna be as of this week. And then the last thing is to see, because you remember I was gonna give, I plan according to the class to give bonus points for those who have reached a particular level of achievement in the class. And I will also make a projection about these bonus points, where we are right now and where we plan to be by the end of the class, because obviously we need to finish it before I see the exact number. But I will give you some projections about that. So 3 things: to write down what I told you we're gonna do, to give you a projection about where we're gonna be in terms of points and what the breakdown is gonna be, or more or less. And then to give you a projection of the bonus points, to give you the bonus points, what you have right now, and then a projection about what other bonus points are coming up. So as I also said, when I look at the points, the top points that where I'm gonna put, say, an A, and then how I'm gonna break it down, I will remove all of the bonus points from that scale. And then so the bonus, and then usually what I do, I take that scale without the bonus points, I grade that, and then on the basis of your bonus, you're gonna move up individually wherever you have to go, all right? So you're gonna have one position without your bonus on that scale, but then with your bonus points, you're gonna move into a different position, and it's the final position that is gonna give you the grade. Okay, so more or less, this is the approach I'm following. Is that understood? Is that clear, what I plan to do?
Yes.
Okay, thank you. All right, so what I would like to do right now, and I'm going to share my screen. Okay. Here, last time, you remember that we talked about this problem. And so I'm doing 2 things. First of all, I would like you, all of these problems that we do, for you to review them. But also what you will see that I have uploaded, what I'm doing for you starting today, is to create a list of things that you will need to do. And so before we come here, because I would like as a review to do the matching network problem here for the 2 we are gonna design today the matching networks. And I have not done anything, so I will do it slowly so you can follow me of how I do it, because for some students, not for everybody, there is still some uncertainty about how we find specific things. So I have decided, instead of preparing them, I will do them real time so you can follow me of how I do that. However, before we come to this, I would like to show you what I have, what I'm preparing for you, and I have uploaded everything. But then every lecture time, I'm going to add material, and I will show you here. So what I'm doing. So I'm describing the approach for the design of an LNA, and I'm putting all of the formulas there. Now, I have checked what I'm writing, but you may also need to check it to make sure that I don't have a typo somewhere. I'm a human being. Sometimes I make typos, and I have that problem. So, but here is how I'm starting. So this will show the problem from the beginning. When you, somebody gives you a transistor and they ask you to make an amplifier out of it, there are specific steps you will take, and it's a long process with lots of steps. That's why it's important to put everything together. There is nothing intellectually complex about it. The only thing is that somebody needs to have all of this information collected. And I will help you do this, put it together, because the book is not very good in describing that. So we start with the stability check. There are two parameters we are going to be looking for the stability check. We talked about only putting the two together in one, but my advice for you is to use these two parameters, K and delta. K has to be above 1, and magnitude of delta has to be below 1 to make sure that the transistor can be stable. If these two apply, then, as it says here, the transistor is considered to be unconditionally stable, which means whatever you choose for your gamma S and whatever you choose for your gamma L, or whatever you choose for your final load, which is Z sub L, and whatever you choose for your source, which is Z sub S, your amplifier is not going to oscillate. That's what it says. So you have freedom in choosing your load, the end load, Z sub L, and the source impedance. However, if one of those two, and usually is the K, that this is not satisfied easily, not the delta, because I don't believe there are people who will design a transistor that has a magnitude of delta above 1, very rarely, and that's because who knows of what problems. Most of transistors that anybody will give you will have magnitude of delta less than 1, but K may or may not be above 1. So if it's above 1, then you are ready to go. If it's not above 1, then you call the transistor, as it says here, conditionally stable. And then in that case, you have to find the place on the Smith chart where you can choose your gamma sub S for the input port and your gamma sub L for the output port. And why is gamma sub L and gamma sub S important? Why are these two reflection coefficients are important? What do you think? Who will tell me? What do these reflection coefficients help us do? Who will tell me? Huh?
I think gamma sub S is important because that's an indication of how much power is getting to the LNA, and then gamma sub L, how much is getting to the actual load.
Right,
Also important for stability and all noise and all that stuff.
right. That is correct. And then because of those two, what are we able to do? If we know gamma sub L and gamma sub S, what can we do afterwards, after that, as soon as we find them? We can design the matching networks, all right? And when you design the matching networks, then practically you have your LNA in place. Now, okay, so the whole goal in a design of LNA is to identify your gamma sub S here, and I will write it, gamma sub S and gamma sub L. That's the whole thing we are trying to do in a design. Obviously, there is not one single value for gamma sub S and gamma sub L, which is gonna make your amplifier stable, all right? So you start with a large area and then you start to narrow the area as you are putting more and more conditions on the amplifier performance. So here is what I would like to do, is to help you see how we do that. Okay, so let's assume that we have an unconditionally stable now. All right, first of all, look at the one case that I have here in the square, this one. That is important. What does this tell you? It tells you that a unilateral transistor S12 is always unconditionally stable. Could you tell me why?
Yes, I can.
Anyone?
I can, because if S12 equals 0, then the K is infinity.
Exactly, goes very, very large, which is a great thing. And delta only becomes the product of S11 and S22, which in 99% of the transistors in magnitude are less than 1. Okay, so practically for all cases of a transistor where S12 is 0, then you know immediately that you have an unconditionally stable transistor. Also, very few times the designer is going to come and tell you that S12 is 0. You know what designers do? All right, designers design for device designers, design a device. All right, they're looking at, for them is important to make sure that the fabrication is the right, that the collector and the emitter and the source is important, or the base, and then or that the gate and the source and what is the other one, the drain, they're all, you know, correctly done, that they have limited parasitics, that they have good materials, that they can fabricate them so the dimensions of the materials are important, and so forth. And then they have the right bias. And then what do? After they design it, then they measure it. They measure it for different biases, and then they measure it over different frequencies. They also design it for high FT and Fmax. And after they fabricate it and they make the measurements, then they give you a list of all of their scattering parameters for various frequencies. And they also, for various bias conditions, all right? They don't necessarily, some may tell you what K is or delta. Many of them will not. So they may give you other characteristics. They will give you gamma optimum, for example, for noise, either low noise devices. They will give you the noise resistance, and they may give you even a maximum available gain at most. But many other things they are not. So it is up to you to find out what the condition of the amplifier is before you start designing. And even if your S12 can be very, very small, that does not mean that you can eliminate it from the beginning without any testing. And if you remember, something that I will add, I have not done so far, but I will add afterwards, is that if you have an S12 which is very, very low, and the designer has not told you that the transistor is unilateral, you have to do a test before you assume that your S12 is 0. And that test is called the unilateral test, where you have a U coefficient, all right? At this point, I have not added, but it's going to be something we are going to do next time. So I'm going to add it in the notes. But what I did here is I went ahead to include what the steps that we follow for conditional stability. And what we said is that there is something that you have to keep in mind, and it's here. Conditional stability circles, they try to help us identify stability areas, not points, areas on the Smith chart. And everything that we identify from stability circles are reflection coefficients. Gamma S for the input stability circles, B1. And in fact, so we talk about the gamma S plane because the input stability circles help us identify areas on the Smith chart in which every point that corresponds to a reflection coefficient can effectively be a point for a gamma S that can make our amplifier stable. However, you have to test for a conditionally stable amplifier. You have to test both the input and the output conditional stabilities, rather. So you have both input circles and output, and that's what I am describing here. So the input stability circles, here are the two equations that give CS and RS, and I say all of the points of the input stability circles represent gamma S values. They don't represent anything else. Every point of this area we identify as a stable area is representing gamma S values, and that's why we call it gamma S plane. So let's assume that we have an example where I found a C sub S here to be 0.5 magnitude and minus 60 degrees phase. And then I found that the radius is 0.4. Okay, now every point, therefore the center, number one, represents a gamma S point. How do we identify reflection coefficient points? So gamma S. I'm going on this circle that says reflection coefficient, you see here. Here. I'm going there, and then I measure 0.5, which is the blue line. I measure 0.5. And then from there, I draw a line, which I have eliminated because it was too complex, but I will draw it here. I draw a line that goes there. And then I'm writing the constant VSWR circle. So why do I call this the constant VSWR circle? Because all the points of this circle have the same reflection, they correspond to the same reflection coefficient, which is 0.5 magnitude. Okay, they have the same, or in other words, all of the points on this circle have the same BSWR. And how is the BSWR? How we have defined the BSWR? You remember? How much is it?
One, yeah.
All right. So since this circle, all of the points on this circle have the same magnitude of gamma. CS is one of these points, all right? But CS not only has a magnitude, which is 0.5, but has a phase, which is minus 60. So how do I find this point? Then I'm going here that says angle of reflection coefficients in degrees, and I'm finding here minus 60. That's minus 60. I draw the line from the center of the Smith chart to minus 60 point, and this is this blue line that I have here. And the intersection between the blue line and the VSWR circle is this point C sub S. So you see it here at the center. Then I'm done with C sub S. I found the point. Then what I need to do is to draw a circle with that center and a radius, which is 0.4. So since all of the points represent reflection coefficients, I'm measuring the magnitude of the reflection coefficient here. So now I'm finding 0.4, which is the magnitude in physical units, at least relatively on the Smith chart, on this Smith chart of the radius. And then I draw a circle. I don't have a compass. So as I said before, everything that I'm doing on the Smith chart using notability is not exact. It's going as close to being exact as I can make it, because it is, you know, it's my own capability of doing that. I don't have a compass, and I don't have exactly a ruler that I can move around, but I think it's close enough. In any case, I'm developing this red circle, and then now I have the red is my CS is my stability circle for the input port. And this is all called the stability plane. However, after I have the circle, I still need to define the area of stability. So here is what this condition, not on S11, but on S22 apply. Even if we are on gamma S, the condition of a scattering parameter is not the scattering parameter on the input port, like it does not have, is not S11, is not S12, is not S21, is S22. So we are watching for the value of S22, and if the magnitude of S22 is less than 1, as in most cases, then the stable region is all of the Smith chart region outside of the circle, the red circle. And that's my stable region. If for some reason people have developed a transistor where the S22 magnitude is above 1, we have not seen one yet, but if for some reason somebody comes with that, then you know that the stable region is going to be the blue one inside the red circle. Okay, so with this, you have now defined the region of your gamma S. So you are done with one side of your amplifier. Now the next thing is to do the output stability circles. Okay, now I give you another example. Let's assume, or maybe the same, but you know, I just made up those values, all right, so you know. So in this case, for this particular transistor, which is hypothetical, CL is 1.2 magnitude, 60 degrees phase, RL is 0.7 in magnitude, always for RL. And now I'm designing what I call the gamma L plane, which means all of the points on the Smith chart represent gamma L points, values. So every point I see on the Smith chart is not an impedance, is not an admittance, is a gamma L, okay? And same way, I measure the blue one that goes beyond. Of course, if you have a ruler, it's gonna be very easy. I made an assumption where it might be. It's not obviously a good assumption, but I placed the CISA best, I assume it's 1.2. So I found the point CISA best, which is outside of the Smith chart, because we know that the size of the Smith chart is still 1. And then I found that R sub S, I was given, I found it, I guess, it says R sub S is 0.7. And I drew this circle that it's part of, in fact, what you see here is just part of a big circle. Okay, so there is an overlap, obviously, between the red circle and the Smith chart. Now, on the gamma plane, I'm looking at S11, not S22, not S12, not S21, S11, on the other side rather. And if S11 is magnitude is less than 1, then it is the outside of the red circle of the Smith chart that is the stable region. But if the magnitude of S11 is larger than 1, is the intersection that is the stable region. And what happens if S11 is larger than 1 and the two circles, the Smith chart and the red circle do not intersect? In fact, here I have to put Isabel. What happens in that case? What do you think?
There's no way to stabilize a transistor?
Exactly. So out of that transistor, you cannot make an amplifier. However, as you will probably learn, I mean, given whatever you are given, all right, knowing that you cannot put a matching network that has resistive elements. All of our matching networks are made out of non-resistive elements. I mean, assuming that you have ideal transmission lines without losses, we don't put resistors, only capacitors or inductors. And that we do that so we don't increase losses, we don't increase noise, because if you have resistors in your matching networks, then practically you are going to have higher noise. It is possible that if in your application you were allowed to introduce resistive elements, that you could make that transistor to be eventually stabilize. You can bring it, you can make the two circles to intersect, assuming that you add somewhere resistive elements. I'm telling you that not for this class, but so you know that if somebody in real life comes to you with a transistor, you do all of this testing and you find the transistor is not stable, no place. You cannot find any, either gamma sub S or gamma sub L. If one of the two does not give you a stable region, then according to what we've learned in this class, you cannot use this for an LNA. However, in real life, if that's the only transistor you have available, you may be able to stabilize it and bring it inside the Smith chart by using resistive elements. So just keep it in mind, we have not learned how to do it, but just keep it in mind that the resistors can give you some possible solutions. Of course, you lose other things. You increase your noise, you lose your gain, and all of this, but you can stabilize it, okay? Now, before we do anything else, at this point, I would like to give you an exercise. And this exercise is available, it's a top hat. So take 5 minutes to look at this exercise and respond to it. And then I will look at this again, and then we'll have a discussion about the responses, and then we'll go and do the matching networks from what we left last time. So, any questions on this before we start with the exercise? Okay, go and do your exercise then. 5 minutes, so it is 2:10 right now. By 2:15, we should have this done.
So it's already on top hat, right?
Yes.
My top hat is still loading.
Okay. Okay, I think we are ready. And I'm going to, it's 2:15. I'm going to turn it off. 1 minute warning. I'll give you 1 more minute, just so you know that I gave you a warning. 1 more minute. Okay, I will unassign it right now. And I will show you what we have. Okay, so here are the correct two answers. Okay. A unilateral, yes.
I just had a quick question about part D. Aren't we allowed
Yes.
to assume that an amplifier is unilateral if we go through the error and find it's less than 0.5 dB?
Yes, but it's an approximation. By definition, a unilateral amplifier always has S12. When you assume that yours is unilateral, is an approximation to simplify your, is not necessarily, all right? It's close to, but by definition, a unilateral amplifier has S12 equals 0.
Okay, I thought we could include the cases where we were approximating.
Okay. This, well,
I wasn't really sure with how the question was worded, I guess.
an approximation is an approximation. To be, I mean, to be precise, I understand your argument, but to be precise, this is the precise answer. The other one is not unilateral. You make the assumption that it is. All right. By definition, the definition of unilateral amplifier is this one.
Okay, I guess it makes sense. If it's less than 0.5 dB, we could assume approximated behavior enough to use the equations, but it's still not a unilateral transistor then?
It's not a unilateral transition. You only make the assumption because it's the regions of, you make the assumption of being unilateral because what happens is that you make your errors of this assumption are small enough, and then it's something you can tolerate while you're making your problem easier. It's not that there is a unilateral transition, a transistor. In a unilateral transition, transistor is one that has S12 equals 0. The other ones are approximations you make, and you will see we'll make all kinds of different approximations when things are not quite what they are. All right. So now you can call it, I have not seen that, but I could call it quasi-unilateral. Quasi, I have not seen that definition. I just made it up. A quasi-unilateral is something that can be considered unilateral without being. And the reason I'm saying that is because we talk about static conditions in waves and then quasi-static conditions in waves. A quasi-static transmission line or a condition is not a static condition, but it's a dynamic field that we assume looks like a static, but it's not a static field. So, however, to be fair to you, I don't know how to give you how to address your concern at this point. But you know, what can I say? The correct thing is D. practically.
Yeah, thank you for the clarification.
Yes,
Dr. Katehi?
yes. And somebody before you, Zahim, was asking for clarification.
Yes, Professor.
Yes.
For number C,
Yes.
just before this, you said that S22 is not, it hasn't been found to be above 1, but it could be theoretically. And I know the book says that unilateral is not always unconditionally stable, because if S22 is greater than 1, then it could be unstable.
Got it. Well, you know, the book has a lot of problems, and I will differ from this because nobody's gonna develop a transistor that has S21 more than 1. Nobody's gonna do that unless they've made a mistake, and they try to force you to use a transistor which is not good. So could you well, how should we do that? I don't want to penalize you for some things that have you know, that are reasonable. Do you like to, for those of you who, how many of you, can you tell me how many of you missed points because of the first case when you thought a unilateral amplifier is not always one that has 1, 2 equals 0, but something that has very small 2?
I also had that thought process.
You did that.
Do you mean that I'm wrong because of A?
A is not correct.
Well, the note says that when it's unconditionally stable, then we just skip part B and directly head into step C, right?
What the question A says, that is an unconditionally stable amplifier does not need an input and output matching network, and that is totally wrong.
So it still needs input matching, input
Of course,
and output
always.
matching network.
Yes, always. Always.
But we don't need to determine it.
Of course, we need to determine it. You don't need to determine the stability regions. But the input and output matching networks, you have to determine them, and we found them from the maximum gain. There are formulas that they're giving those to.
Oh,
So
okay.
yeah, you always have to use input and output matching networks.
Okay.
But okay, well, listen, what we are gonna do. Because of these various concerns, I like the discussion we had because it gives me an opportunity to clarify some things. All right, I will give those who responded, not those who didn't. I will not. I will help you with the points. I'm gonna give you those that you missed. I will not give points to those who did not respond. However, however, I want you to remember one thing. That number 1 in A, an unconditionally stable amplifier always needs, and if you want to do an amplifier out of a transistor, you always need to have an input and you always need to have an output matching network, period. Okay, that is period. Number 1. An unconditionally stable amplifier does not always has S1 to 0 or equal to 0. You can have an unconditionally stable amplifier and your S12 can be very different than 0. That's number 2, from those who indicated that was correct. A unilateral amplifier is always unconditionally stable, assuming that you have transistors, which I always assume, and you will see in every single application that you may find. If you find a transistor that is somebody has developed with S22 higher than 1, please show it to me. If you find ever. I don't know why they would have developed it, but it may be for some reason that I don't know. All of the transistors that are practically made, S22 magnitude is less than 1. Maybe very close, but less than 1, definitely. So In any case, a unilateral amplifier remembers that. Remember that a unilateral amplifier, transistor rather, or amplifier in that case, since it's part of the transistor is part of this, is always unconditionally stable. And a unilateral amplifier, a true unilateral amplifier, has S12 equals to 1. A quasi-unilateral amplifier is one that has S12 different than, one I said 0, I meant, S12 different than 0, but something that you can ignore because your error when you make that assumption is small enough, okay? And we're gonna talk about this. So if you remember those things, that I'm happy with this exercise, and I will give you the points for just going through the experience to respond to it. Okay, now I think we are 2:20, I forgot, but I will do what we spent time clarifying that, but I think it's worth spending. I will continue the solution of the matching for the matching networks rather, input and output. For the previous problem, I will continue this afternoon from 3 to 4, but we are gonna record it, so I will put it up on eCampus for those of you who cannot come and see the solution for the matching networks. Any questions?
I'm sorry, Professor, I didn't catch that last.
Which one?
I didn't catch the last thing you said.
The last thing that I said is that I'm going to record the solution of the matching networks input and output from the last lecture's problem. I will do it from 3 to 4 today. I will record the solution and I will upload the recording on eCampus. So for those of you who cannot come to office hours from 3 to 4, you can still see the solution. Okay. Thank you so much. Yes.
Where will
Okay.
that recording be posted eventually? Will it be
So,
posted on the weekly modules?
Yes, usually I don't post them immediately. It takes me some time to download them.
Right.
And then I have to remove the times. I have to do some processing, so you don't have to go through. But I was hoping by Wednesday I will have it up.
Oh, no, I was asking where specifically on eCampus.
On eCampus. I will create a new module that is called to review for final. And I will have all of these review sessions there.
Okay, great, thank you.
Sure. Okay, so I will see you in about half an hour. Thank you.